If somebody can confirm that it's recording, this is Math341 lecture, let's call it 28. What I want to do today is talk a little bit about coding. So the problem we're going to do is the tic-tac-toe problem. I'm going to talk a little bit about how you can do it in some greater generality. As always, I have a secondary window over here to just do some calculations. All right? 9 factorial. 362,880. Large, yes.
Is it possible to do a little bit of the theory and then segue into the coding as to kind of a transition, or are you just doing straight coding?
I'll be talking about a little bit about the theory as we do it, but the theory is pretty straightforward.
Okay.
So, but there is a theory thing that I want to remark that's not in the solution key. So is this number a large number, yes or no?
Yes, but not for a computer. Yeah.
Not for a computer, depending on what you're doing. If you're just doing very simple calculations, 362,000 is not a big deal. If each calculation requires 10 to the 8 things to do, it's huge. With everything in life, it's always relative. But if your calculations are simple, this isn't so bad. So your question was to analyze the 3x3 random tic-tac-toe game. Best way to do it is brute force to calculate the probability of winning, and then to do a computer code to simulate it. Now you want to make sure your code is correct. Are you going to go through all possible tic-tac-toe games? What could you do to try to get a sense of whether or not your code is correct?
Bring in smaller sections and print the...
So one thing is to print out stuff going in small sections and make sure that it's doing what you're doing. But I assigned the 3x3 tic-tac-toe game. What could you have started with?
2 by 2.
2 by 2. Now instead of 9 factorial, what would we have with the 2 by 2 game? We'd have 4 factorial. If you cannot do 4 factorial by brute force, then you have what do I want to use? You have a bad sense of what is a reasonable question to ask. 24 cases by hand is not so bad. How many moves are there, initial moves are there in two-dimensional tic-tac-toe? How many opening moves are there in two-dimensional tic-tac-toe? 1. So it gets better and better. Only 1 move to start 2 by 2. Right? How many responses are there? 2 responses. So there's not that many things to consider. What is the probability, do you think, that somebody wins in two-dimensional tic-tac-toe? And if so, who do you think could win? Yes?
First person wins every game.
First person wins every game. There's no way they can lose? So if you think about it, there is no way the first person can lose. No matter where they go, doesn't matter where O goes to stop, any square, they could get the diagonal win if necessary, they could get row, they could get column. They can't lose. Okay? So while there's strategies for two-dimensional, for three-dimensional tic-tac-toe, two-dimensional, it's pretty straightforward. Player 1 wins. So if you write your code in generality, you can then test it on two-dimensional tic-tac-toe. And if you don't see player 1 wins 100% of the time, you've got a mistake somewhere. If player wins 100% of the time, does that mean you coded it correctly? No, sadly it doesn't go that way. But if you don't see 100%, you know you made a mistake. All right, so let's write the program. So this is general tic-tac-toe. All right. And I'm going to have a couple of parameters. So simulate and num iterations. So as always, I start and end of modules. And so here, simulate equals 1 if simulating, else brute force. So this is to allow me to do one code that will solve both cases. Either randomly simulate or go through and enumerate every single possibility. Now in the solution key I gave you, I simulated it in a cheating way. What I did is I created a list of all possible tic-tac-toe games. That's only 362,880. and then I randomly choose a number between 1 and 362,880, and then that's the game I choose to play. I'm not randomly choosing moves. If I wanted to do 4-dimensional tic-tac-toe, do you think this is doable? What number do I need to look at for 4-dimensional tic-tac-toe? All right, so let's go to 16 factorial. And if I do 16 factorial, okay, let's get a sense of how bad that is. So I'll take the log of this number, base 10. Okay, oops, it goes the other way around. I always forget which way you do the base first or second. So I want the log base 10 of 16 factorial. So it's about 13. So this is 10 to the 13. Even if I play some games and try to save some time about where that first move is, there's not that many possibilities for a 4x4 board, it's still going to be too much for a good brute force. Okay? So for the theory, we can get by with 2 and 3. Can't really get by with 4. I am going to ignore 1-dimensional tic-tac-toe, the 1x1 game. This is really, really not worth studying. All right. And then again, it's not bad when you're coding to say, num iterations is the number of times we go through. Notice that this is only going to be in play if we're doing the simulation. If we're not doing the simulation, if we're doing the brute force, we are going to not really care about num iterations because we're going to just do everything. So in fact, I need one more variable. I need the size of the board that I'm going to do. Doing it on size by size for the board. Okay. Is this a good size text for people to see? All right, we're not going to be able to get the entire code on it, but all right. So now I'm going to let when 1 equals 0, when 2 equals 0, keeps track of wins. Okay, so I'll just keep track of how many times player 1 wins, how many times player 2 wins. And since I know how many games are played, I already know how many ties there are. I could have another one that keeps track of ties, but I'm fine with that. All right, so big list, I'm sorry, here. So list is going to be empty. And then in the 3x3 case, I just brute force wrote what the list was. And so my list in the 3x3 case was list was equal to 1, 1, 1, 2, 1, 3, 2, 1, etc., etc., etc. That's what I did in the 3-dimensional case. I could have written code to create the list. Why didn't I write code to create the list? The list only has 9 elements. I can type it so fast. But if I'm doing the general case now, I will want to do that. So now I'll go for I equals 1, I less than equal to size, I plus plus, for j equals 1, j less than equal to size, j plus plus, and then list equals append to list I comma j. So creates the list for the game. Or maybe I should say board. Let's test and make sure that this code works. So what I'm going to do is I'm going to take this code, I'll paste it over here. Can people still read that? And now what I'm going to do is I'm going to print out list. And what do you think is going to happen when I print out list?
An empty list.
Why?
What size?
What size? It has no idea what size is. So I need to tell it what size is. So over here, let me just say size equals 3. And now when I do that, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, if I make size equal to 4, oops, I have to reprint out the list, sorry. And now it prints out the list. So this just allows me to know that I actually am creating the list as I want. I have my board as I want. So the theory for how I'm going to do things is I'm going to play a game. And when it's player 1's turn, I'm going to put in a 1. And when player 2 turn, I'm going to put in a 10. Let me just change the size. So okay, for game, we'll do 1 for player 1, 10 for player 2. And we've got to be a little bit careful.
As there X's and O's?
Mm-hmm.
Okay.
And what I want to be able to do is I'm going to look at a sum in a row. And if the sum equals 3, player 1 wins. If the sum equals 30, player 2 wins. That's fine if I'm doing it on a 3x3 board. But now I have a board of length size. I've got to make sure things stay separated.
Perhaps would it be easier if 10 was 0?
Well, I'm going to initialize the entire board to be zeros. So any square where there's no move is going to be a 0.
Okay.
So I've got to make sure when I'm on a 3x3 board, your 3 1s will be well separated from 3 10s. And I don't have to worry about, what if I have a bunch of 1s and a 10? So I want to just make sure that I can't ever have something coming. So for instance, let's say I was on a 12x12 board.
Mm-hmm.
If I'm on a 12x12, if I had 2 1s and 1 10 adds to 12. I could think player 1 has just 1. So I can't just use 1 and 10 now. I've got to make sure that they're well separated, yes.
Well, what if you do 1 times size and 10 times size? So if you make...
So I'm going to just be safe. I'll do 10 to the size. Yes?
Why can't you just do -1 over 2?
I tell you. So if we do negative 1s, I think that actually might work very nicely. So the only way that you could get a sum all the way up to size is if they're all, so that's even better. So email me for that. That's even better.
Hell yeah.
-1 for player 2. And so now, I guess the reason I didn't like that is because that is implicitly assigning a negative connotation to player 2, that they're not as good as player 1. But, I mean, we all know player 2 is not as good as player 1. I mean, have they made a book, Ready Player 2? No. Hollywood knows this, okay? So, it's true. So, we will assign a -1 to player 2. And now we just have to check and see, does a row ever sum to 1? Does a row ever sum to -1? Does a column or does a diagonal? Okay, so now what we want to do is we want to start getting ready. So we have our list, that's going to be our initial board. And now we're going to do if simulate equals 0, then big list is going to be permutations of list. So if brute force store all games. Right? So we are only going to do this step. So we'll do if 0 brute force. So I could even have a statement over here. Yes?
What does the permutations command do?
So this lists all permutations of lists. So for instance, if I do permutations of list right now, there's insufficient memory?
Because you're doing it on 4.
Ah, yes. Okay, so let's redo it at 3. Yep. And so now, list is back down to 3. There we go. And so now, it's going to try to do all of that. Yes.
So in every game, we're storing every game.
And then we're going to analyze each game one at a time.
In terms of the storage, could you also, if you're going to run this like a million times, could you also check to see if someone wins and then just like add 1 to win 1 and then go through it again so you don't have to store every single game?
Right, so the way we're doing it right now is memory intensive.
Mm-hmm.
So if we had fast computers able to do a 4x4 board, this is a bad way to do it because we are using so much memory.
Yeah.
But notice it didn't take that long to create all the permutations. It took a couple of seconds. I've got the memory to store it. So I'm going to be lazy, and in the case when we're doing it by brute force, I'm going to actually have it just store all the games. This is not great programming, but for what we're doing, it's fine. If you wanted to do it in more generalities, what you would have to do is you would have to go through all the different permutations. And you would have to then find a way to code going through all the different permutations. This is easier. I'll put a little right here, if simulate is, let's say, is greater than 1, print bad choice of simulate. Just to warn myself now that I might be putting in something other than 0, 1. Right? So for me, 0 is going to be brute force, 1 is going to be just do things randomly. So if simulate equals 0, I am going to just store everything in big list.
You want to close the if statement.
Did I not close it? Thank you. Okay. Actually, I've never saved this yet. So Tic-Tac-Toe general. Okay. So now we've saved Tic-Tac-Toe general. I've come over here now. Now what I'm going to do is numDo is going to equal, let's see, if simulate equals 1, numDo is going to equal num iterations, else numDo is going to be size factorial. So this sets how many times we do. And now we save it in the same variable, numDo. Okay?
Besides squared factorial?
I'm sorry?
Size squared factorial?
Oh, yes, thank you. So size times size factorial, thank you. Okay, so far no code errors in terms of running it. So now we are ready to start the big loop. All right. So for n equals 1, n less than or equal to numDo n plus plus, begin end of for loop, of n for loop. So again, always start and end your loops as soon as you can. Make it clear where it starts, make it clear where it ends. I'm going to put a print statement just so we have some idea of how much we've done. If mod n, and then I'll do numDo divided by 10 equals 0, print we have done 100 times n divided by numDo %. So this is just a print statement, so we have some rough idea of how much of the game we've done. So it's going to print out every 10%. Prints out status every 10%. Okay? So now what we want to do is we now want to start deciding how we're going to play the game. So we first are going to have to start doing moves. And then after we start doing moves, we're going to have to constantly be checking to see, is the game over? All right. So the first thing is we have to load in a game, or we have to randomly choose a game. So let's call this maybe game. So if simulate equals 1, then we need a random game. So game will be random. I think random sample list, and then let's see. So when I do random sample like this, I get something with the exact right number of elements. If I did list comma 6, it would give me something of size 6. If I do list comma 9, it will give me something of size 9. If I don't put the 9 there, it just assumes I want everything. If you're not sure what a command is, you do question mark random sample, and it starts telling you what things are. You can click on the double greater than, it'll give you more information. You can scroll down. You can click on scope, applications, various things like that. So this will give me a random game.
So it's like if they were just picking all these random games that we created, because so that will give us the same result as if we alternated player 1 and player 2 and found out all the.
Right. So what I'm doing here is I have all the elements of the board, and I randomly order the elements of the board, and that's going to be how the game is played. The first element. So over here in this game, the first player goes in position 2-3. Player 2 responds by going in 1-1. Player 2 responds in 1-1. Player 1 goes in square 3-3. Player 2 goes in square 3-1. Player 1 goes in square 1-2, and so on and so on. What we're doing is we're actually enumerating the entire game. Even after somebody gets 3 in a row, we still know what would happen. So what happened with the Red Sox and Dodgers this year?
Red Sox won.
In how many games?
5.
Who was the MVP?
Steve Pierce.
One of my friends just missed $5,000 in trivia last night because nobody on the team knew who got the MVP. I will tell him that if he had anybody, I know. They were in Australia, so the fact that they even knew what baseball was is not bad. So how many games did the Sox beat the Dodgers in? 5 games. Right.
They won 4.
They won 4 games. They won games 1, 2, lost game 3, won game 4, won game 5. These are best of 7 series. First 1 to 4 wins. Games 6 and 7 aren't being played. We could, if we want, just assign what had happened in those games. And then in terms of evaluating who wins the series, as soon as somebody gets to 4 wins, we stop. But it might be easier to just assign all the values initially. And that's what we're doing over here. We are putting in all possible moves until the board is completely filled. We may not need to go that far. So if we're simulating, we randomly choose a game. And if we're not simulating, then game is going to be big list, and we'll just choose game N. So I think that closed off here. Okay. So randomly choose a game or take the next brute force game. Okay. So any questions about what we're doing here? So now we've chosen our game. Now we just have to start putting the stuff in. So the first thing is we need to normalize our board, and then we're going to start putting things in. So we're going to have to do this every single time. So since n goes from 1 to num2, every time we start a game, we have to reset the board. So reset game board. We have list of moves now. So for I equals 1, I less than equal to size. For j equals 1, j less than equal to size, I'll make board I comma j equals 0. So I'm going to be doing this as an array. Initialize all board squares to 0. No one took. Right. So now we're going to start putting in the moves. We're going to put in moves from player 1, we're going to put in moves from player 2, and we're going to check and see, did anybody ever win? Right. What we've got to be careful about is to make sure we exit the games as soon as possible. We want to minimize runtime. As soon as somebody has won the game, you stop. The Sox and the Dodgers did not play games 6 and 7. When I flew back during game 5, and I met somebody in the airport in Albany who had tickets to game 6. And he was torn, because he really wanted to see the Sox win, and he really wanted to go to game 6 and see the Sox win there. You don't keep playing. So as soon as you can abort a calculation, abort the calculation. Don't have your computer doing things you don't care about. So I'm going to create a variable called came over. I'm going to initialize it to be 0. So make this 1 as soon as game done. Okay? And that will allow us to stop a little bit early. The next thing is num move is going to be 0. So this keeps track of what move we are on. Because we now have to start loading in the game. So what's the maximum number of moves we could have?
9.
I'm sorry?
9.
Not 9. Because we're doing things in general now.
Oh.
So you're close. So it's
Size? No.
size squared. So we need to do some kind of looping. So I used a while loop here rather than doing a for loop. A while loop is actually not a bad way to do it. So I'm going to do while num moves is less than size squared and game over is less than 1. End of while loop. So I could have had a counting variable. Maybe m for moves is the move I'm on. And I just keep counting. For m goes from 1 to whatever. This way I can at least show you what a while loop is. It's good to see different kinds of ways of doing things. All right, so now what I want to do is I want to play until I run out of moves or until somebody wins. So play till run out of moves or someone wins. And before we run the program, who do you think has a better chance of winning, player 1 or player 2?
Player 1.
Player 1. There should be an advantage to going first. Worst case, just go in the upper left-hand corner. Just forget about your move. So clearly, when you're playing randomly, player 2 can't have a better chance than player 1. What do you think happens as the size of the board gets larger and larger and larger?
It becomes more fair.
It becomes more fair. Do you think it's going to converge to 50-50?
No, because there's a tie. So.
Yeah, so do you think it's going to become very likely to have a tie, or as n gets very large, do you think that there's a limiting positive probability of win? My feeling is it's going to be so hard to have everything in a row, column, or diagonal if n is going to infinity that my gut feeling is it should go to 0. I don't know if anybody's proven this. If you're interested in some extra credit, Google this and try to see, has anybody calculated these probabilities for n by n tic-tac-toe? All right, so we're going to play until somebody runs out. Okay, so now the first thing I'm going to do is num moves equals num moves plus 1. Making a move. Okay, and we initialize num moves to be 0, so we started off with no moves. So as soon as we go through the while loop, every single time at the very beginning, we increment our move by 1. So now we need to load in our current move. So I'm going to call current move will be, what variable am I using? Am I using game? So I will do game, and then I need to be careful. Which element of game do I want to call in? So right now, we've game. I'll do as a random sample of list. So we have our game. So which element of game do I want to call in? Oh, was it out of focus? Thank you. Which element of game do I want to call in?
Element num moves.
Element num moves. Num moves is my current move. It's going to start off at move 1. So the first move I'll call in this one. So I want to call in num moves. So loads move. So the x coordinate will be current move, and I'm just making sure I use the right language, 1, and then y will be current move 2, the first coordinate and second coordinate. So to just check these things, let's, over here I'm going to set num moves equals to 1, and then I'll plug in x and y. When you put a semicolon, it suppresses the output. So I'm going to just remove the semicolon so we can actually see the outputs.
What is the x and y?
Just I'm trying to just read in the x coordinate and the y coordinate. Okay, so, okay, oops, game is a list. So I actually want to do double brackets. And now everything is fine. So I called in the first move. So this is why you test things. And now I can say, oh, I dropped the double brackets. And so here's my current move. Here's my x coordinate, here's my y coordinate. And now what I can do is we've initialized the board to be empty, right? So now we'll do if mod num moves 2 equals 1. So if it's an odd number, then I want board at xy to equal 1. Else I want board at xy to be what? Negative 1. Oops. And
You said else? Do you actually need to write an else statement in here?
Nope. So the way if works in Mathematica is if this condition is true, you do this, else you do this.
We'll just put the comma.
You just put the comma.
Okay.
So this adds move to board. So we've now put the board in. Okay? So we are almost done with the code. So now the hard part is we now need to just check and see if anybody has won, right? So we have to check that before we end the while loop. Check to see if someone has won. Is it possible that two different players could have won on the same move? No. Is it possible that one person could win multiple ways with the same move?
Yeah.
Yes. Imagine you have two idiots playing tic-tac-toe on a 3x3 board, and the first person loves the corners. And on their first 4 moves, they take all 4 corners. And the second person loves the middles. And on their first 4 moves, takes all the middles. And yes, this game could happen, and I know this error actually hurts some people in their code. And then on the last turn, player 1 goes in the middle and gets 2 X's for both diagonals. So all we need to do now is see if somebody wins. So let's initialize win to be 0. And now we'll check to see if somebody won. So we can do it several ways. So for I equals 1, I less than equal to size, we're going to check our rows. Okay? And then what we'll do is if the sum of ij, j goes from 1 to size, equals 1, I'm sorry, not equals size. Oh, there's a trick we could do. I have to check to see if it equals size or minus size. What else could I just do? How can I check to see if it equals size or minus size in one check? Absolute value, right? Remember sending an email. Let's just take the absolute value of the sum, not the sum of the absolute values. So we're doing this. So, okay, sum I. Let me just, okay. So now what I want to do is if the absolute value of the sum, and now what I want is I want board ij, right? And I'm going to have j goes from 1 to size. And if that equals size, then win equals win plus 1. All right, so I think I missed a bracket here. Okay, there we go. And then ends I for loop. Okay, so now what we're going to do is we're going to check, we fix an I. So I is going to be 1, 2, 3. It's going to be our row. And then j goes from 1 to size, so we go straight down. So this is going to give us a column. Is the first column equal to plus or minus size? Is the second column? Is the third column? And if yes, somebody won. If not, okay. Now what do we have to check next?
Which thing was switch I and J?
Yeah, so this checks columns. So now all we need to do is for j equals 1, j less equal size. Oh, whoops. I need an I plus plus here, right? J less equal to size, j plus plus.
But having two for loops separated, does that check to see if someone checks until someone wins in the columns, and then checks to see if someone wins?
Correct. And so I could be a little bit better that as soon as one of these equals size, I could actually abort and stop doing the rest of the checks. I want to make sure we finish the coding today, so I'm not going to put stuff like that. You could make the program a little bit better. For instance, once I find that somebody won, I can stop. Yes?
Would someone win both by row and by column?
Doesn't matter. All I care about is if somebody won.
Would that double count?
It would, no, because I'm just, yes, so win will still be larger. All I care about is win greater than 0. So in fact, if you want, we can just make win equal 1. We don't really care how many times people have won. We can just do it like that. And so now what else do we have to check? Diagonals. So now, if the absolute value of the sum of board I goes from 1 to size, equals size, then win equals 1. Now what do we have to do? Right, absolute value of sum of board. Now you just got to be careful how we want to do it. So I think it's size plus 1 minus I, and then I'll go the opposite. I goes from 1 to size. If that equals size, then win equals 1. So I've left something out.
What is that count?
Just 1 second. Just going in the opposite diagonal.
So just to clarify, in a 4x4, to win you would need 4 in a row?
Correct.
Okay, great.
So board. Okay, there. And so now that will check the two diagonals. So if I equals 1, we start off with the point size 1. Then we'll get size minus 1, 2. And when I equals size, then we get 1 comma size. So this is going to go through the opposite. Okay? So now, if win is greater than 0, end if statement on win. So now we have to do a couple of things if win is equal to 0. The first is we had game over, I think. So we're going to make, oops. The first thing we do is make game over equal 1. Someone won. Now we need to record who wins. If mod num moves 2 equals 1, then player 1 got the win. Right? Else player 2 got the win.
Isn't that going to record a win for 1 if it's a tie with 9 moves?
I'm sorry?
If it's a tie with 9 moves?
Well, no, I'm only doing this if win is greater than 0.
Oh, that's within the...
Right, this is within the win loop. So if win is greater than 0, then I'm going to increase either player 1 or player 2, depending on whether or not I'm at even or odd. Okay. Any questions on this? So I think now all we need to do is just print out the wins. So I think I have the code. Just print out the stuff here. So let's just save some time and just paste this in. So if simulate equals 1, I'm going to print out that we're simulating, and this is the number of trials we're doing. Else I'm going to say we're printing out all possibilities. So then we print out percentage of time player 1, 1, percentage of time player 2, 1. All right. So question, yes?
I think the print statement is still inside the...
Oh, is it still inside? Oh, did I put it too high? I think, yes, you're right. Thank you. Good catch. So we do not want to be putting this every single time. So we want to get this outside the end loop at the very end. So hopefully there's no errors here. So for the code, it's simulate number of iterations and size. So let's do simulate. Let's do 10 iterations, and let's do a 2x2 board. And so you start off with something small, and I'm going to put a timing just so we have some idea of how long this takes. I'm very worried that it took 10% of the time to do this. So there's got to be then some small mistake somewhere.
Just print out.
It should not be taking this long.
Nothing should be
On
after.
a 2x2 board?
It did the first one and then it got stuck.
Right. So it's
maybe something wrong with the while loop.
so
Do you ever increase the num moves at the end?
we did that very beginning. Num moves equals num moves plus 1.
Maybe.
Right, so this is why you always start with a very small code. So now we need to start putting in some print statements. So let's quickly check and see if we can see what's going on. If num moves equals 2, board xy equals 1, else board xy equals negative 1. So we're adding moves. Win equals 0. Then we go through. Oh, wait a minute. Okay. And then as soon as win is greater than 0, we come in here. Okay, we have game over. So it's got game over in blue, so I'm just wondering if there's some kind of... So let's see. We have a num over here. I think that should be maybe num do. That should be num do. So I don't like the fact that game over is in blue. The big list is also in blue.
What is blue?
Oh wait, if simulate, that should be a lowercase. And this is one of the issues. All right, and then where was big list created? Big list. Okay, so let's try that. All right, so that was one mistake. If simulate equals 1, game is random sample list, else game is big list. So let's make simulate. All right, so it's definitely storing all the games in big list.
Did you miss any plus pluses? Because there was one time halfway
So
through.
that's a good thing to look for. So n goes from 1 to num do in steps of size 1. If simulate equals 1, I equals, here we go. Email me for extra credit. I plus plus. For j equals 1, j plus plus.
Oh, is that 2 emails?
No, because I got the second one. All right, so let's see if that works. All right, so now there's a protected tag somewhere. Are we calling it win? Oh, we called it win. I thought we called it one. All right. So we have to just change this to wins, because we then used win later on. So when we come over here, we can't use wins in two places. All right. So so now over here we just change this to wins, 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 wins.
Above, two more above.
Two more. Which one?
Left.
Left. Yep.
Yeah.
Okay, yep.
And right above.
Yep. All right, there we go. And so in the 2x2 case, we're now getting, and we have, 2.5 minutes to spare, not even close. All right, so with the 2x2 case, we're getting 100% of the time that player one wins. All right. We can also, instead, we can do it by theory and brute force enumeration. All right. So now, let's go back to simulate, and let's do a 3x3 board. We'll do 1,000 times. Those are the probabilities you should get. Let's go to a 4x4 board, which is now something we haven't done before. 37, 26, and about 41. All right. Let's go to a 5x5 board. Let's go to a 10x10 board. All right. Now we're seeing it's actually taking some time. So it is playing 1,000 10x10 games. How many of you have seen the movie War Games, Matthew Broderick? Good movie. All right. So now, player one wins 1.3% of the time, player two wins 1.1% of the time, and 97.6% of the time, it is a tie.
How small do you think the probabilities would get if we did like 100,000 by 100,000?
Well, so that's then the question is, what is the rate of decay? I believe that those probabilities are going to zero. You can start calculating, what's the probability that somebody gets everything in a row? Well, each label has a 50-50 chance if you want, although as soon as you start assigning some labels to player one, then it becomes more likely that other labels are player two because you have to give them moves. But if the board is huge for a given row, you can do some rough estimates to get decay rates. Okay? But this should be enough to give you, some sense. And this took us 17 seconds. So if I want to go up to, 20, I'm now doubling the size of the board, quadrupling the size of the board because it's quadratic. So you might think maybe is it on the order of a factor of 4 times. So instead of taking 17 seconds, I think maybe it will take a minute.
You haven't even got 10% yet.
Haven't even gotten 10% yet. But this is the power of writing general code, is rather than just in studying the one case we did, we can now look at lots of things. Okay, so now it's got 10%. So I will just let it keep recording so that it will at least output the result of the 20x20 case. That shouldn't take too much longer to finish. All right, bless you. So again, I hope this was useful in terms of helping you get a sense of how do you attack a problem like this. All right.
I worked so long on this, and I can't believe you got through the general case in under an hour.
If you consider how old you are,
Yeah,
and the fact that I've been a professor longer than you've been alive,
that is true.
and I've been coding since I was maybe
I
5 or
have
6.
All right.
Oh, are these the answers to the...
So those are the answers.
Okay.
This is the homework.
That's the homework.
Yeah, obviously, like I said, I'm new, and I'm
Yeah.
still in R because...
Yeah, which is fine.
But I had to... We went to R tutors and every week learning about while loops. And
Yes, but that's a skill that I want you to have.
It's slowly growing.
But this is why I have not given you that extensive of a homework assignment. I want you to really spend the time, and I want you to have this as a skill. This is extremely valuable. And as a theorist, to look and get some sense of the rate of which these numbers are going to zero, I would do some kind of plot and then try to estimate.
I do have a side question.
Yes.
So when I signed up for Ridley over the summer,
Yes.
my mom said, "Oh, that's so funny because her and her best friend who lives down the street every night play like 10, 15 games of backgammon."
Okay.
And she's like, and they recorded who wins every
Yes.
time.
They record the opening roll.
No.
Okay.
Maybe, I don't know. But she wants me to see whether or not they both are terrible and they're like basically like random.
Right.
One person is better than the other because they have so many. So I think you could just do like a null hypothesis
Well,
or something.
what I would like you to have them do is the following. You start recording the roll
Yeah.
and who goes
70%.
first.
They have like 500 samples now that they've done.
Right, but I'm saying, but they don't have the key information.
Yeah.
So for instance, do you play the following? If both people roll sixes, you have to re-roll. Let's say you roll a 6 and then the other person rolls a 1. Whoever goes first gets the 6 and 1, or do they get to roll the die?
Okay. Yeah.
Which way do they play?
I have no idea, but it would be. I mean, it would be. Considering how I literally did brute force like coding
Right.
on the last one, this would be even more complicated. But it is interesting. That'd be kind of cool.
But what I'd love to do is I'd love to then do an analysis and
Yeah.
say, for instance, how many times are you winning because you went first and got a really good roll,
Yeah.
versus you went second and the person who went first had a really bad roll.
Yeah. I'll
So if they can start recording that information, I'm happy to do the analysis.
Awesome. Okay.
Yes.
You emailed me all the homework.
Yes.
Ask you about intention, like
Yep.
during the weekend.
That's fine.
Turning up on
Yep,
data.
that's fine.
Sure.
Absolutely fine. It's just I don't always remember what I promised people, and
Yeah,
so my
yeah.
habit is to just always when I got you to so we had talked about something.
Jesus.
Okay.
Oh, wow.
What happened?
So
Actually 1-0, actually. So
Right.
what would that say about the theoretical mean? Because that's really small, 20.
we're only doing 1,000 trials.
Right, but I'm saying you only did 20 by 20, so what if you did a 100 million by 100 million?
Oh, I mean,
You're getting 0 by a 20 by 20.
you're getting 0 to maybe 2 or 3 decimals.
Right, but you're going to make everything bigger by a size
Correct.
of 10
Right.
million.
Right. My feeling is it's got to go to 0.
Speaking of which.
Nice. Nice. All right. Let me just stop the recording.
I'll call her right now. Let her
Yeah.
know.
No.